Welcome to Math with Professor V. This is video lecture for section 3.1 for business calculus on limits. So to motivate the idea of what a limit is, we're going to work through the following exercise. I want you to consider what the values of f of x equals x squared plus 2 are near x equals 2. So not at x equals 2, but near it. Well, what do we mean by near? Well, let's look at some options. Getting increasingly close to 2, and you tell me what it looks like things are going towards, okay? So here I have a little table set up, and these values are pretty close or near to 2. 1, 1.5, 1.9. In fact, let's throw one more in for good measure. How about 1.99? Why not? These are all values that are smaller, right, than 2. And then 2.1, 2.5, 3, and 4, those are all values that are bigger than 2, but they're pretty close. So let's see what the y values are now if I substitute in each of these x values into the function f of x given right here. X squared plus 2, okay? Oh, I wanted a box, not an arrow, for crying out loud. Okay, there we go. So let's start plugging stuff in. 1 for x, f of 1 is going to be 1 squared plus 2, that's 3. 1.5 squared plus 2, that's 4.25. 1.9 squared plus 2, that's 5.61. And 1.99, 5.9601. Okay, right now, where does it look like the function values, the y values are going? Where are they heading? They're getting bigger. And then here it looks like they're getting really close to 6. Okay, let me put that on pause. Now let's plug in the values that are a little bit bigger than 2 and see. So 2.1 squared plus 2 is 6.41. 2.5 squared plus 2, 8.25. 3, we get 11, and 4, 18. So these values are further from 6, but notice as we get closer and closer to 2, again, the function values, the y values, seem to be approaching 6. So it looks like if we were to actually substitute in x equals 2, which we're going to do in just a hot second, right now I already have a feeling that f of x looks like it should be 6. And indeed it is. We can confirm f of 2 is 2 squared plus 2, which is 4 plus 2, which is 6. Okay? Now you might say, Professor V, this feels like a waste of time. I could have just plugged in 2 and seen that the function value was 6. I know, that's great. But later we're going to understand that in some cases you can't actually plug in or substitute the value of x that you're approaching into the function immediately, but you can still observe via the graph or other algebraic methods what the limit is approaching. So this is going somewhere. Hang tight. Let's plot this too while we're at it. We did parabolas not too long ago, right? Remember we reviewed quadratic functions. So f of x equals x squared plus 2. That's a parabola opening upwards. Let me scale my axes. I'll do the y-axis by 2. So 2, 4, 6, 8. And then x, we can just leave it scaled by 1. So, okay? And, you know, I'm not crazy about all the values on this table because it's got so many little decimals in there. I'm just going to plug in some nice stuff. So 0, 2, 1, 3, that's fine. And then negative 1, 3 would also be on there. And then we have 2, 6, negative 2, 6 would also be on the graph. So here's our gorgeous parabola. Love it. And we could see here, yes, the function values, the y values, were approaching 6 from both sides of the graph, from values that were smaller than x equals 2 and values that were larger than x equals 2. So now when we're talking in terms of limits, if we're looking at x values that are smaller than what we're approaching, we say that we're approaching from the left of that x value. And then when we're looking at values that are bigger, right, these were all bigger than 2, we say these are from the right. And why do we use the terms left and right? Well, because we're thinking in terms of the x-axis, right? We were approaching x equals 2. So if you're coming from values that are smaller, you're coming from the left side on the x-axis. Yes, from the left. If you're coming from values of x that are larger than 2, then you're coming from the right side. And this will come into play later on, okay? You'll have to pay attention to which side you're approaching from. So let's summarize our findings, and then we're going to learn some function notation. Here we can state the following. We observe that as x values approach 2 from the left, then f of x or y values approach, what did we say? These were all from the left, and it looked like the y values were going where? To 6. Very good. And then as x values approach 2 from the right, same thing, f of x approaches 6. So when we can say this, that the value of the limit is the same from the left and from the right, then we write that the limit as x approaches 2 of f of x equals 6. So this is probably brand new notation. We write lim to indicate we're taking the limit. This is always x approaching something. It's your independent variable, usually x. Sometimes it could be t or something like that. And then you have your function. And then this equals always the y value where the function is heading, what it's approaching. Okay, so this is the limit here. So the way you would read this out loud, in case you've never seen this before, is you would say the limit as x approaches 2 of f of x is 6. Good. That the is a little squished. Forgive me. You wouldn't know what it says if I hadn't read it out loud to you. Okay. And then we have a way of indicating whether or not we're approaching a certain x value from the left or from the right. And it's by using a plus and a minus sign. So notice here, if we're approaching from the left, we write x approaches 2. You see that little minus sign? That means from values smaller than 2, from the left side of f of x. And then if you're approaching from the right, then you put a plus sign from values that are larger than 2. And you're going to see in some examples coming up why it's important to pay attention to which side, okay? So now let's look at a definition. We say the limit as x approaches a of f of x equals L if we can make the values of f of x arbitrarily close to L by taking x sufficiently close to a, but x isn't necessarily equal to a. X does not equal a. And there's 3 cases where the limit as x approaches a of f of x is equal to L. So L is always the y value. This is the function value. You see how L is indicated on the y-axis? But like I mentioned earlier, it's not always as straightforward as just plugging in the value that x is approaching into the function. I want you to see the examples that are happening here. So here, first case, yes, straightforward example. The actual function value at a is equal to L. And that's the same thing as what the limit of the function is as x approaches a. Okay, that's great. Now look here at the second case. Notice, let me zoom in. There's an open circle. So the function is not defined to be L when x is equal to a. In fact, if I said, what is f of a equal to? Well, it's equal to whatever the y value is right there. Let's call it m. So I'd say f of a is equal to m. But we're not interested in what the actual y value is when we're talking about a limit. The idea of a limit is, where are you heading? What is the y value that you're approaching when you're actually walking on the graph? So say you tell your friend, hey, I'm going to walk over to x equals a, and they go, cool, I'll meet you there. Well, where are they going to try to find you? You're like, I'm walking over to x equals a. Looks like you're heading to y equals L. So they're like, hey, I'm going to come meet you too. And you're going to meet up. You're going to meet up at y equals L. So it doesn't matter what the actual function value is. When you're walking on the graph, where you're heading, the y value that you're approaching is the value of the limit. And if you and your friend can meet up at the same spot, regardless of which way you were walking on the graph, then we're good to go. The limit exists and it's equal to L. Ooh, I know that was a lot. Okay, we'll look at one more case here where the limit does exist and it's equal to L. And notice here, there's an open circle and there's no closed circle anywhere. So f of a is actually not even defined. It's undefined. But if you told your friend, hey, I'm walking over to x equals a, come meet me there. I'm coming from the right side, and your friend's like, cool, I'm gonna come from the left and I'll meet you there. Are you meeting up at the same spot? Yes. You're both approaching y equals L. And it doesn't matter that when you actually get there, there's a hole in the graph. The function is not defined there. You guys were heading to the same y value. So the limit exists, and we say the limit as x approaches a of f of x equals L. So that's why limits are not always as straightforward as just plugging in or substituting in a into the function, because the limit isn't necessarily equal to the function value there. Okay, it can be. The first case it was, right? In this very first case it was, but it doesn't have to be. Okay, so let's build on this idea a little bit more. Here's a different graph, and I want you to use the graph below to find the limit as x approaches 0 of f of x and the limit as x approaches 2 of f of x. So we're going to look at two different x values. What we're going to do is break it down and look at the limit from each side of those x values. So first, let's consider x equals 0. We're going to look at the limit as x approaches 0 from the right of f of x, and then the limit as x approaches 0 from the left of f of x, okay? So you're walking towards x equals 0, you're walking on the graph, and you're coming from the right side. So on the right side of the graph means values that are bigger than 0. You're coming from over here, and you're having a grand old time walking towards x equals 0. Now your friend is walking on the other side. Will you guys meet up? Let's see. You're on the right side. What y value are you heading towards once you get very, very close to x equals 0? What's the y value that you're approaching? It's 0. It sure is. Now what about your friend coming from the left-hand side? They're over here. They're walking on the graph, heading towards x equals 0. What y value are they heading towards? They're also heading towards y equals 0. The limit is the y value. These are the y values. Are you guys going to meet up? Are you going to be able to get a coffee or whatnot? You sure are. So we're going to say, all right, the limit as x approaches 0, this is now a two-sided limit because I'm not writing from the left or from the right, and I don't need to because they're the same. So the limit as x approaches 0 of f of x is equal to 0. Okay? If you ever see something like this written, a two-sided limit, and it equals some number, that's because you can assume the limit from the left is equal to the limit from the right. But you have to check that for yourself if it's not stated. See here, they told us to find this limit. So before I can do that, I have to check that it's the same from both sides. Good? Okay, now let's look at what's going on as we approach 2. And we have to do the same thing. So let's look at the limit as x approaches 2 from the left of f of x, and then we'll look at the limit as x approaches 2 from the right of f of x. Okay, let's get these people out of here so they don't confuse us. So 2 from the left. So from values smaller than 2, you're walking on the graph here. What y value are you heading towards? The limit is the y value. It looks like you're heading towards y equals -2, doesn't it? Okay. What about your friend? They're coming from the right side of 2, over here, walking on the graph. Always walking on the graph. You can't be like floating out in no man's land. No, you only walk on the graph. Everything else is hot lava. Let's just say that. Where are they heading? What y value are they approaching? Yeah, they're heading towards y equals 1. So that's the value of the limit. Oh no, are you two going to be able to meet up for a coffee, for a gelato? No. -2 does not equal 1. These are not equal. So since they're not the same, then we say the limit as x approaches 2 of f of x. We don't put equals because it doesn't equal anything. We just say it does not exist. So DNE we use as an abbreviation often to represent that a limit does not exist. So anytime the limit from the left does not equal to the limit from the right, then we say the limit does not exist, the two-sided limit, okay? All right, now, we're not always going to be able or have graphs at our disposal to compute limits, so we want to be able to look at the equation of a function and compute the limit using that. And so we're going to need to first establish some limit laws in order to do so. So here are our limit laws. Suppose the limit as x approaches a of f of x and the limit as x approaches a of g of x exists. Then the following is true. So the limit of the sum of the functions is equal to the sum of the limit of each of them individually. So that just basically means like you can distribute a limit across addition, subtraction. If you have a constant times a function, you can basically take the constant out of the limit and just find the limit, then multiply by that constant. The limit of a product of functions is equal to the product of their limits. Same thing for a quotient, just make sure the denominator is not 0. We'll talk about what to do if it is. You can also take the limit of a function raised to some power, pass the limit inside, and then raise all of that to the nth power. The limit of a constant is just equal to that constant c. So I want to demonstrate this using a graph just so that it makes sense to you. For example, say we had the limit as x approaches, I'm going to make up something, 3, and my function is going to be a constant, 7. This is just going to equal 7. And you might say, that seems a little bizarre. I know. Well, remember, this is f of x, right? Well, f of x is the same as saying y, and y equals 7. Do you remember what that's the graph of? It's just a horizontal line, right? We reviewed graphing lines earlier. Horizontal line means the slope is 0, and it's just going to cross through y-axis at 0, 7. So it'll just look something like this at 7. Well, the limit as x approaches 3 would be over here, it's 7. I mean, no matter where you go on the graph, you can run back and forth to your heart's desire. Your y value, your function value is always 7. It's not changing. So that's why the limit of a constant function is just equal to that constant. Doesn't even matter where x is going, okay? Also, the limit as x approaches a of x is equal to a. So if you had something like the limit as x approaches 3 of x, that would just be 3. Again, you could graph, this is the line y equals x, slope 1 goes through the origin, or are you ready for this? You could just think, I'm plugging in 3 for x, boom, there's 3, okay? So these two are important, we'll be referencing them. I mean, they're all important though. And then the limit as x approaches a of x to the n is equal to a to the n, where n is a positive integer. So again, you can basically just think I'm substituting in a for x. And same thing, if x approaches a of the nth root of x, then that's equal to the nth root of a, as long as n is a positive integer and a is positive when n is even. Also, you could take the nth root of a function and pass the limit underneath. And f of x equaling g of x implies that the limit as x approaches a of f of x equals the limit as x approaches a of g of x when x is different from a. Okay, so here's all your limit laws. We'll be referencing them, but you don't need to like make flashcards or something and be able to write them down that way. Just know how to apply them. All right. First thing we're going to talk about is the direct substitution property. So if your function is a polynomial or a rational function, and a, remember x approaches a, that's the x value, is in the domain of f, then the limit as x approaches a of f of x equals f of a. Literally just plug in a for x. Okay, so let's practice a little bit here. We have the limit as x approaches 2. Notice this is a rational function, 2x squared plus 1 over x squared plus 6x minus 4. So we're just going to substitute in, direct substitution, plug in 2 for x. So this is 2 times 2 squared plus 1 over 2 squared plus 6 times 2 minus 4. So in the numerator, 2 times 2 squared plus 1, that's going to give me 9. Over 4 plus 12 minus 4, that's 12. So that's going to simplify to 3/4, and we're done. That's our limit. Pretty straightforward, right? Okay, next example. Evaluate the limit if it exists. We have the limit as x approaches 1 of x cubed minus 1 over x squared minus 1. So again, I have a rational function. Let me try to just directly substitute in x equals 1. So we would have 1 cubed minus 1 over 1 squared minus 1. Uh-oh, this is giving me problems because I would have 0 over 0. Oh no, that's an indeterminate form, meaning I can't determine what the limit is when it's written this way, 0 over 0. So what we're going to do, and a common technique to keep in mind when this happens, is try to factor your rational expression and see if you can cancel something out that'll get rid of the problem, those zeros in the top and bottom. So let's try factoring. Do you know how to factor the numerator? It's a sum of cubes. You may have forgotten. I'll link a video here. Click, it's in the top right, how to factor a sum or difference of cubes. So the numerator is a difference of cubes. Excuse me if I said sum earlier, I can't remember. A cubed minus b cubed factors into a minus b times a squared plus ab plus b squared. And I use the acronym SOAP to remind me of the signs. So you always have the same sign as what's in the OG binomial that you're trying to factor. And then you have the opposite sign next. So if we started with a minus, now we have a plus. And then the last one's always positive. So there's your SOAP, S-O-A-P. And then the other thing you do need to just remember is the pattern. So if you have a cubed minus b cubed, ab, a squared, ab, b squared. No extra constants in the middle, okay? Good. So then how would x cubed minus 1 factor? It would be x minus 1, x squared plus x times 1, so just x plus 1 squared, which is 1. So that's how we're going to rewrite the numerator. And then let's go ahead, take a glance at the denominator. It's x squared minus 1. That's a difference of squares. You can factor that hopefully, yeah? Oh, good. So x squared minus 1 factors into x minus 1 times x plus 1. Okay, now I'm excited because look, I can definitely cancel out x minus 1 here. And then you have to keep rewriting lim every step of the way until you have actually plugged in 1 for x and there's no more x's in this function here, okay? So, oh, there's still x's, so here I am still writing lim. X squared plus x plus 1 over x plus 1. All right, now let's try plugging in 1. So this is 1 squared plus 1 over 1 plus 1. Oh, yay, we're going to get a number this time. So we have 3 over 2. And we are done. Okay, so the most common mistakes I see that students make, they stop writing lim along the way. And then they write it too much. At this step, there shouldn't be a lim anymore because there's no more x's. I've already evaluated the limit. I just need to simplify it, okay? So if there's no more, this is x is going to 1. So as long as there's x's, you got to write lim. There's no more x's, don't write it. And this is new, so just practice, but be precise because a lot of students lose points. The math police will come snatch you up if your notation's not on point for calculus, okay? All right, let's look at some more examples. Here we have the limit as x approaches 4 of x squared minus 4x over x squared minus 3x minus 4. Now, always try to just substitute or plug in the value that x is approaching first. So here x is approaching 4. So let's just try 4 squared minus 4 times 4 over, that's crooked, 4 squared minus 12 minus 4. Nope, 0 over 0. We're in trouble. So let's see. Can we factor this guy? limit x approaches 4. Yeah, I can take x out of both terms in the numerator. So I have x times x minus 4. And then how does the denominator factor? X squared minus 3x minus 4. Oh, okay, yeah, good. X minus 4 times x plus 1. Notice, yay, again, we can cancel out x minus 4. I still have to write lim in the next step. Lim x approaches 4. Now I have x over x plus 1. Okay, good. If I substitute in 4, can we evaluate the limit? Yes, 4 over 4 plus 1, that's 4/5. Perfect. Notice I didn't write lim once I actually plugged in 4 for x, right? Beautiful. Very good, you guys. Okay, let's look at another example. The limit as x approaches -1 of x squared minus 4x over x squared minus 3x minus 4. So this time x is approaching -1 instead of 4, same function. So let's see, if we just directly substitute, are we going to be in business? -1 squared minus 4 times -1 over -1 squared minus 3 times -1, so plus 3 minus 4. So what do we have going on? I have +1 plus 4, so I have 5 in the numerator, over 1 plus 3, that's 4 minus 4, that's 0. So 5 divided by 0, what's going on there? Well, what we're going to learn is that anytime your numerator is a constant but not 0, okay? So we just looked at the one previous, we had 0 over 0. This is called an indeterminate form. Okay. This is different because we don't have a 0 on the top. We have some other number over 0. What happens here is this is going to approach either positive infinity or negative infinity. And if we can't figure out which one, then we just say it doesn't exist. And in this class, you're not going to have to get too rigorous with infinite limits. If you're a pure calculus like STEM major, then you are going to need to understand this topic more thoroughly. So I have a video dedicated to infinite limits. I'll link it here, but you only need it if you're just interested in understanding limits thoroughly beyond what's necessary for a business calculus course. And if you're a regular calculus student, you're going to need Calc 1 and 2 and maybe 3, then this is not the video playlist for you. Okay, you should be watching just the regular Calculus 1 video lectures. Okay, back to the point though. Let's see if we can simplify first, if that's going to help us. Because remember, factoring and canceling got us somewhere. I'm hopeful maybe it'll work again. So we have limit x goes to -1. In the numerator, let's take an x out. We've done this before. And then, yeah, I remember that x minus 4 canceled. Cool. And then you have limit x approaches -1 of x over x plus 1. Did that fix it? No, I'm so sorry. We've got -1 over 0. Again, we have some non-zero number over 0. What the heck? Well, remember earlier when we were studying rational functions, we said after your function was reduced in lowest terms, wherever the denominator is 0, we had a vertical asymptote. So hopefully you're remembering, okay, we have a vertical asymptote at x equals -1. Which makes sense then that the limit's going to be either positive infinity or negative infinity. So I actually happen to have the graph here of the function x squared minus 4x over x squared minus 3x minus 4. I just got this from desmos.com. Desmos. You can go to their webpage or they have a nice free app, okay? And I plotted the function. Now you can see here, x equals -1. They don't put the vertical asymptote in for you, but there it is. And notice it depends which side we're approaching from. So if I were to say, what's the limit as x approaches -1 from the left of f of x, what would you say? So you're walking on the graph, heading towards -1, but you're on the left side. What y value are you heading towards? Oh yeah, up, 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 up. Forever and ever, you're heading towards positive infinity. Now what's the limit as x approaches -1 from the right of f of x? So now you're on the other side of the graph, walking, heading towards -1. Where are you going? All the way down to -infinity. So notice the limit from the left of -1 is not the same as the limit from the right of -1. So that's why we say in this case, the limit as x approaches -1 of f of x does not exist, okay? If they had both gone to positive infinity or both gone to negative infinity, then I would have written that as my answer. Technically, limits have to be finite numbers, but even if the limit isn't finite, we can just specify and tell the people, hey, it's going here. It doesn't exist as a finite number, but just in case you were curious what the graph looks like, I've got some info for you, you know? Okay, so in grand conclusion, based off of the graph, we're going to say this limit does not exist, okay? Now, in the other video for pure calculus students, I show you how you can just do that by hand without a graph at your disposal, okay? Very good. Let's look at another example where we're going to have this non-zero over zero infinity situation come up. So find the limit as x approaches -2 of f of x, where f of x equals 3x plus 2 over 2x plus 4. I have the graph here, but say you were to start off trying to do it by hand. So you're doing the limit as x approaches -2 of 3x plus 2 over 2x plus 4. So you should always try just to substitute or plug in the value that x is approaching. So I'm like, okay, 3 times -2 plus 2 over 2 times -2 plus 4. In the top, I'm going to have -6 plus 4, so that's -4 over, 0. Yeah, so same thing. Again, you can tell we're going to have a vertical asymptote when 2x plus 4 equals 0, which would mean at x equals -2. So it makes sense the graph is going to approach positive or negative infinity. So this is why we're going to have to look at both sides. So what's the limit as x approaches -2 from the left? So here's x equals -2. From the left, going to positive infinity. And then from the right, where are we going? Yes, excellent. You're going to negative infinity. So what do we say? The limit from the left does not equal the limit from the right. So therefore the limit as x approaches -2, you have to always write f of x or the actual function that it's equal to. So if you don't write f of x, you could write 3x plus 2 over 2x plus 4. I doubt you want to do that much writing, but you can't just write nothing here, okay? That's wrong. It does not exist. Okay, good. That's our answer. And don't put equals does not exist. It doesn't equal anything. It doesn't equal anything. Very good. I know this is all new. When I first learned limits in calculus, I was like, what in the world is going on? I always thought I was good at math, and this feels bizarre. It was unsettling. That's what it was. So if you're feeling that way right now, don't worry. It'll go away. This is new, so have no fear. Okay, couple spicier examples. Find the limit as x approaches 0 of 1 over x plus 2 minus 1/2. So if we just try to substitute in 0 for x, I'd get 1 over 0 plus 2, so 1/2 minus 1/2 over 0. Uh-oh, this is 0 over 0. No good. So what to do? Well, one thing I'm noticing is this is a complex fraction, meaning we have a fraction inside a fraction in the top of a fraction. So that's a big no-no. That's considered not simplified in math. So what should we do? Let's try to get rid of those extra fractions, get rid of the extra denominators. And the best way to do that is just multiply by the LCD. So I'm going to multiply the whole fraction, top and bottom, by x plus 2 and 2. You have to do it in the top and bottom. That way you're just multiplying by 1. You're not doing anything illegal that the math police might come and snatch you up for. So x plus 2 and 2 distributes across the numerator. Now I'm going to have lim x approaches 0, 1 over x plus 2 times x plus 2 times 2. The x plus 2 cancels. So you're just going to have 2 minus, and then now this 2 will cancel in the next term. So I just have x plus 2. But don't forget parentheses. Watch out. Don't forget the parentheses. Those are my watch out eyeballs. And then in the denominator, I just have x times x plus 2 times 2. I'll write that as 2x times x plus 2. It'll look better. Okay, so now let's clean up. Limit x approaches 0, 2 minus x minus 2 over 2x times x plus 2. Ooh, these 2's cancel now. So then I have the limit as x approaches 0 of negative x over 2x times x plus 2. Anything you notice? Yeah, we can cancel out this x with the x in the denominator. I still have a negative in the numerator. It's actually negative 1, right? So limit x goes to 0, negative 1 over 2 times x plus 2. Oh my goodness. Can we finally plug in 0 for x and get something? Yes, we can. All our hard work has not been in vain. Negative 1 over 2 times 0 plus 2. So negative 1/4. Woohoo! Box it with pride. Yes, we made it. We made it. Okay, so just as a heads up, because this is probably the first time you've seen anything like this, when you have a complex expression, try clearing out the extra denominators and then see, usually some fabulous factoring will occur along the way that lets you cancel and whatnot, okay? Good. One more example. We have limit as x approaches 36 of rad x minus 6 over x minus 36. So if you try to just plug in 36, can you see how you get 0 over 0? I know, so problematic. So one technique that we often use when you see radicals is we multiply by the conjugate, top and bottom. So the conjugate of rad x plus 6 would be rad, I said it by accident. The conjugate of rad x minus 6 is rad x plus 6. I got too excited. Cat's out of the bag. Okay, so we say a plus b and a minus b are conjugate pairs. Or conjugates. Why are we excited about them? We love them because a plus b times a minus b, their product is a difference of 2 squares, which is great when you have a radical because then it gets rid of the radical sign, and that's what we're hoping for. So I can rewrite this as the limit. X approaches 36. In the numerator, we don't actually need to sit there and FOIL this all out because they're conjugate pairs. I know I'm going to end up with a squared minus b squared. So a squared is rad x squared, that's just x, minus b squared, which is 6, so b squared is 36. Beautiful. And then in the denominator, don't multiply it out. Oh my goodness, please don't. Let me say this. 99% of the time in your math career, you will not multiply out the denominator. You want the denominator factored. You usually only multiply out and factor and play around with the numerator, not the denominator, okay? So leave this alone. Leave it in all its factored glory. And hopefully you can see why, right? Because x minus 36 from the numerator cancels with x minus 36 in the denominator. Hooray! So what are we left with? There's a 1 up top, isn't there? Don't forget about that. Over rad x plus 6. Whew! Can I plug in 36 for x now? Yes, yes you can. So we have 1 over rad 36, that's 6 plus 6. So this limit is 1 over 12. Hooray! Okay, good. One more new idea with limits. And we have an important theorem here. It says the limit as x approaches infinity of 1 over x to the r is equal to 0. And then same thing if x is going to negative infinity, as long as r is greater than 0 and it's a rational number. So basically what this means is if you have 1 or actually any constant in the numerator and the denominator is getting really, really big, either in the positive or the negative direction, your limit's going to come out to 0. And that should make sense because like 1 divided by 100 versus 1 divided by 1,000,000 versus 1 divided by 1,000,000,000, it's going to get so teeny tiny, it's going to be insignificant or basically 0. And it doesn't matter if you're dividing by something positive or negative. Okay? So how is this useful to us? Well, when we're finding limits now, you see how x is going to infinity? It's not going to a number. We're switching things up, people. Yes, we are. Well, when we're trying to compute limits of this form and we have a rational function or just top's getting big, bottom's getting big, the technique that you want to use is divide the numerator and denominator, so everybody, by the degree or the highest power of the variable that you see of the denominator. So not overall, just from the denominator. Okay, we're going to practice right now, don't you worry. And actually, we intuitively talked about this. I don't know if you remember when we were looking at the average cost function in a previous lesson, and it said, what does the average cost approach as x gets arbitrarily large? Well, we were taking a limit and we talked about how one of the terms approached 0. So it was basically because of this reason. Okay, here we go. So first example, find the limit as x approaches infinity of 3x plus 5 over x minus 4. So what I'm going to do is divide everybody by the highest power of x from the denominator, which is x to the first. So everybody gets divided by x. Cool? Yes, we have to rewrite lim as x goes to infinity. The first time, since this is the first example, I'm going to really walk it through step by step, and then I'll show you kind of if you want to simplify a few things in your head for the next ones, okay? So limit x goes to infinity. This is 3x over x plus 5 over x. Then we have x over x minus 4 over x. Okay, so this is the limit. X goes to infinity. Let's clean up a bit. 3x over x, that's 3. 5 over x just stays. X over x is 1 minus 4 over x. Now this next step you don't really need to do ever, but I'm just going to write it to show you the thought process. We know that from our limit laws, we can distribute a limit across a sum and across a fraction, a quotient. So that's exactly what I'm doing, but in my real life when I do limits, I don't write this out. I just want you to see what's happening. So we're going to take the limit of each of the terms. That's all. So the limit of a constant, doesn't matter where x is going, is a constant, plus as x goes to infinity, where does 5 over x go? Well, it doesn't matter if there's a 5 or there's a 1. If this is getting super big, this is going to 0. It doesn't matter if you multiply it by 5, okay? And then, so we've got a big old 0 up here. Over this 1, this is just a constant, so he's hanging out. I'm 1, you can't touch me. Minus, where's 4 over x going? It's going to 0 too. The 4 isn't going to do anything important. So 3 plus 0 over 1 minus 0, that's just 3. Okay, but for the next problem, I'm not going to write out this step. You don't need to. You can just go from here. You want to see what you could do? Of course, Professor V, we don't want to write extra steps. What are you thinking? You just go, oh, this guy goes to 0, this guy goes to 0, and then all I'm left with is 3 over 1, 3. Boom. Nice, huh? Okay, so here, let's try another example. Divide by the highest power of the variable from the denominator. So what am I going to divide by? Yes, t cubed. Divide by t cubed. Good job. So here we go. We've got limit. T approaches negative infinity. In the numerator, I'm going to have t squared over t cubed plus 2 over t cubed. And then in the denominator, we've got 1 plus t squared over t cubed minus 1 over t cubed. Okay, let's clean up. limit t goes to negative infinity. Usually I just jump to this next step that I'm writing out here. I'll already simplify in one shot. 1 over t plus 2 over t cubed. And then this is 1 plus 1 over t minus 1 over t cubed. Usually I just go straight to there. So as t goes to negative infinity, remember, it doesn't matter if it's positive or negative infinity. If you have a constant in the top, top's not changing, and the bottom's getting really, really big, everybody's going to 0. The 1 stays put, everybody else goes to 0. So I'm left with a 0 in the numerator over 1. That's just 0. Okay, 0 in the denominator is problematic. 0 in the numerator is not. I think it was a student told me this, that they heard like their high school teacher say, if you have an egg and you put it on top of a table, it's fine. But if you have a table and you try to put it on top of an egg, it's problematic. Okay. All right. Last one of this kind. We have limit as x approaches positive infinity, x cubed minus 2x plus 3 over 5 minus 2x squared. Now notice here the limit's going to infinity, that's fine. But also keep in mind, we're only going to divide by the highest power of x from the denominator. So I don't care there's an x cubed up top. We're dividing by x squared, highest power from the bottom, okay? And then let's see, can you simplify in one step? I think so. Limit x goes to infinity. The numerator is going to be x minus 2 over x plus 3 over x squared. And the denominator? Yeah, 5 over x squared minus 2. Good. So if x goes to infinity, 2 over x is going to go to 0, 3 over x squared is going to go to 0, and 5 over x squared is going to go to 0. You could do either. You see how I circled and wrote to 0, or you can slash through them. You know, you live your life. Still going to write out lim. X goes to infinity. Now, who didn't go to 0? Who's still surviving here in this limit? Surviving and thriving. We have an x and we have a negative 2 in the bottom, right? Yeah. So as x goes to infinity, the numerator is going to infinity, but then I'm dividing by a negative number. So it's still going to get really, really big. It doesn't mean if you divide infinity by 2, it's still infinity, right? It's getting big. But because we're dividing by negative 2, that is going to change the sign. So this limit ends up equaling negative infinity. Whew. Okay, that one was a little funky, but just go through it again slowly on your own. You know, after you finish watching this video, make sure you can replicate the steps and then you should be in business. Okay, last type of function that we're going to look at for now and find limits of are piecewise defined functions. If you're having a really rough time graphing piecewise functions, you are not alone. Oh my goodness. All of my calculus students and pre-calc struggle with this. So I have an extra video on graphing piecewise functions. I'll link it here. Just click in the top right and in the description. It'll help you. And I show you how to make a table if you need it. Right now, I'm not going to do that because we want to just focus on limits. And hopefully the functions are straightforward, but I show in that video a nice method if you're just really on the struggle bus with this. Okay, so don't feel badly. There is hope. There's light at the end of the tunnel. So we need the limit as x approaches 0 of f of x. I'm graphing it. Let's graph it and use the graph. So 1, 2, 3, 4, 5. You know what, let me spread it out more. And make it go a little lower. Okay. I have to go to negative 2. And then 1, 2, 3, 4, 5, 6, 7. Okay. And then 1, 2, 3, 1, 2, 3. So the function is equal to 5, y equals 5, horizontal line, if x is less than 0. Notice it's not inclusive. So we're going to have an open circle at 0, 5. X value is less than 0 means to the left, and put an arrow here. It's without bound. Now, between 0 and 3, this is a parabola, x squared minus 2. I'm just going to put a few numbers in my head and plot them. So if x actually equals 0, 0 squared minus 2, that's negative 2. That's down here. Then 1 squared minus 2, that's negative 1. So we've got 1, negative 1. 2 squared minus 2, that's 2. Okay, and then if x is 3, 3 squared minus 2 is 7. So that's going to be right here. So we've got the parabola coming through. Boom, boom. Now, last part of the piecewise function says if x is greater than 3, f of x, or y, is equal to 7. So another horizontal line. Notice this 3 is not inclusive. So you have like an open circle, but we never draw an open circle on top of a closed circle. That's just weird. So since there's already a closed circle there, you just don't do anything. And then you're going to show that the function, or y, equals 7 to the right. Okay, good. All right, let's use this fabulous graph to answer the following questions. Find the limit as x approaches 0 of f of x. So notice the way the function was defined switched at 0, so we have to check both sides of it. So let's look at what's the limit as x approaches 0 from the left, and then what's the limit as x approaches 0 from the right of f of x. Okay, let's see. So from the left of 0, here's x equals 0. From the left, we're over here on this part of the graph, just chilling. We're heading towards y equals 5, yes. Now what about from the right side of 0? You're on this part of the graph. What y value are you heading towards? You're heading towards negative 2. Uh-oh, the limit from the left doesn't equal the limit from the right. So then we say the limit as x approaches 0 of f of x does not exist. Oh. Okay. What about the limit as x approaches 3? Do we need to check from both sides of 3? We do, because see, again, 3 is where the domain split. It's switched equations, so we have to check both sides of 3. So let's see, what's the limit as x approaches 3 from the left of f of x? And then what's the limit as x approaches 3 from the right of f of x? So from the left of 3, we're here. What y value are we heading towards? We're heading towards 7. Now, if I'm on the right side of 3, I'm over here. Where am I heading? Towards 7 again. Ooh, okay. We're heading towards the same place. So the limit as x approaches 3 of f of x equals 7. Very good. Beautiful work. Now, this isn't on there, but I just want to make a point. Say they asked you for the limit as x approaches 2 of f of x. Now look at your piecewise function. 2 is not where it switched how it was being defined, right? What makes something a piecewise function is you take different functions and you paste them together. And we're not sure that at the places where they're like pasted together, was it done so that the limits match up or not? But if you're at somewhere that's not a cutting point, right, not where the domain splits, like 2 is clearly in the middle, it's on x squared minus 2, I don't have to check from both sides. Nothing was chopped up or pasted together right here. So no paranoia, you just go, oh, I'm just gonna say it's 2 squared minus 2, so 4 minus 2, it should be 2. See, it's 2. There's no way it would be anything different, okay? So for piecewise functions, just pay attention if they're asking you for the limit as x is going towards somewhere where it's switched equations at that x value, then you got to check from both sides. But if it's not, right, if it's not spicy point 0 or 3, then just plug it in to the appropriate place and move on with your life. So that was so much information. Good job if you made it to the end. I hope you enjoyed this lesson. And like I said, limits are just so unnerving at first, and then you'll become comfortable, okay? You'll get used to them. They won't be so strange. I hope you enjoyed the video though. Give it a thumbs up. Subscribe if you haven't already. And like I mentioned, a bunch of extra videos. If you want more resources, I'll also link them in the description. I have full video lectures for calculus 1, 2, 3, stats, pre-calc, trig, all sorts of stuff. And you can also follow me on Instagram, TikTok, Twitter, Math with Professor V. Thanks you guys so much for your support. I love you all, and I'll be back sooner than later. Bye.